Okay, hi everyone. This is our first video in chapter 2, so section 1, chapter 2, section 1. And this is really going to be a very high level introduction to quantum mechanics. And what we are trying to do is understand where the energy exists within molecules. Because where we are going is that by the end of chapter 3, we want to be able to say if we know the energy contained in one molecule and we have a sample of a mole of molecules, how much energy is in that sample? And so that's kind of where we're going. And so to get there, we have to first understand where does the energy exist within molecules. Okay, so note for this video, you are not expected to perform any calculations with any of these equations. You need to understand the concepts of where the energy is stored. And to this point, there is not a now try this problem to go with this material because this is background knowledge and concepts that we need to understand, but not skills or problems that we need to solve. Okay, so we're going to start with the general chemistry view of quantized energy levels. At one point in Gen Chem, we started talking about light and about how electrons only exist at certain energies within the atom. And this led us to the idea of electron configuration. Remember saying that the electron configuration is 1s2, 2s2, 2p6, etc., and that each of these electrons existed at a particular energy and that they could only have those particular energies. So this is still true. These electrons in atoms do have quantized energies. And as those of you who have taken instrumental at this point know that we talk a lot about transitions that can occur between these energy levels, these energy states, if an electron receives enough energy. And we talk about how the transitions only occur between specific energy states. So if our electron exists here in the ground state, then we can't happen to put energy in and get our electron to exist here in the middle. Middle isn't an option. It has to get excited up into this excited state and land on that other energy level. Kind of like a ladder. You don't get to step, or stairs. You don't get to step halfway in between and expect to be able to exist. So that was our Gen Chem view, in that we have these energy levels. But it turns out that as we get a bigger picture and we have a better view of what these atoms and molecules, we're going to talk specifically about molecules. So not atoms, just molecules. There are 4 types of energy that molecules can have, ways that molecules store the energy. They can have electronic energy, vibrational energy, rotational energy, and translational energy. And the total energy in our molecule is just the sum of these 4 types of energy. Okay, so to start off with, we're going to kind of go from the biggest contribution of the energy to the smallest contribution of the energy. So, in Gen Chem, we talked 1s2, 2s2. Turns out that is very good for atoms. But once we start thinking about molecules, things get a lot more complicated. And we have to find the answers. We have to solve some tough quantum mechanics problems, which we're not going to do. That's for next semester. So to figure out the electronic energy, we use something known as the particle in a box. And what we do is we assume that we have, in this case, we're going to assume a three-dimensional box. This could be a sphere as well. A box makes the math a little bit easier than a sphere. And inside of this box, we put a particle. Let's just call our particle an electron, just for the sake of working with, because we're chemists, we like electrons. So in this, we say that the electron cannot leave this box, and this box represents our molecule or our atom. It turns out that we can solve these equations for either atoms or molecules, but so we're going to use that interchangeably. So electrons cannot leave, and these electrons are going to occupy this defined geometry that we set. And if we do this, we solve this out, we get that the energy, this is the electronic energy, has an equation that we can calculate. Okay, so there's some variables here. H is going to be the this is Planck's constant. M is going to be our mass. V is the volume of our container, or the size of our atom. And N is the energy level. And so this N is really thinking about the 1s2, the 2s2, which quantized energy we are. And if we map this out, where on our x-axis we have this, or I'm sorry, on our y-axis we have energy, which I can't spell, and we can map out the states that come out, the different energies of the states that come out from our calculation. And you see that there are lots of possibilities. Okay, so the take-home message here is that we have an equation to calculate the electronic energy of a molecule or an atom. Well, okay, great. How do we know this is real? Well, it turns out that we can do UV vis or fluorescence spectroscopy, and these energy states that we start seeing are the energy states that we call the highest occupied molecular orbital and the lowest unoccupied molecular orbital in MO theory. And so if you think back to organic, you would talk about how our highest occupied molecular orbital has electrons in it. We add light, and those electrons can transition to the lowest unoccupied molecular orbital. And when those transitions happen, we get absorption. Okay? So another way that molecules, and in this case only molecules, contain energy is in vibrations. And so how do we figure this out? We use what's known as the harmonic approximation. And in this, we treat atoms as masses attached by a spring. And so this means that we have something like H, hydrogen, and chloride, and this bond between them is a spring. And then we can use the math, we can describe the spring the same way that you would in physics using Hooke's law. And the result becomes that every electronic level contains a set of vibrational levels. So let's be more specific. So the answer to the harmonic approximation is that the vibrational energy is equal to V. This is the vibrational energy level, plus a half times omega E, and this is the frequency of the vibration. And so when we say frequency of the vibration, we are talking about how many oscillations per unit time we get. And so we're really talking about going from state A to state B and back again. So this is compressed, so a shorter bond, to expanded, to a longer bond, and back again. And omega E has a way of calculating. K is the force constant. Mu is the reduced mass. H bar is a version of Planck's constant. We factor in 2 pi into it to make it easier on our equations, but it's a version. And so with this, we can get the omega E and the energy of vibration. What does this look like? We've been drawing some energy level diagrams and some pictures. Well, so what we really have is this well shape, this parabola shape, that represents our electronic energy level. And within that electronic energy level, there are quantized vibrational levels. Where do we see this? This is infrared spectroscopy. The wave numbers, the energies of these motions, are the E vibrational value. So our OH stretch has a vibrational energy. Wave numbers is proportional to energy. It's a energy unit of 2971 wave numbers. So our E vibrational in this case is that. That is for our OH stretch. Okay, so we made it through electronic, vibrational, now rotational. And so this is energy that is stored in these molecules as they spin. And how we do this is we treat the atoms as if they're attached by a stick, not a spring. We are using a rigid rotor approximation. So we are now ignoring the fact that we just assumed that the bond was a spring, and now we assume that this bond cannot move. And then we treat this as a rotating body, just like we would in classical physics. And our answer is that every vibrational level contains a set of rotational levels. And so rotations are quantized energy, and they are given by, so this is the rotational energy, is given by Bj, j plus 1, where B is the rotational constant and J is the rotational energy level. And so we get the series of quantized energies that our molecule can have when they're rotating. And things like this rotational constant, this is an experimentally determined, well, there's also a way to calculate it, but we're not going to go there. That's for next semester. Okay, the final type of energy is translational energy. This is the easiest one because it's actually not quantized. And translational energy is defined as the kinetic energy of the molecule. And so just like your car can go any speed that it wants, well, sort of within limits, but it's not like you have to jump from 10 miles an hour to 50 miles an hour. You can go 10, 11, 12, all the way up. Translational energy is the same way, that there's no set energies of kinetic energy that the molecules have to have. And kinetic energy is determined as 1/2 mv squared, where v is the velocity, m is the mass, and EK is kinetic energy, also known, in this case, for molecules as translational. Okay, so put it all together. If we think about this total picture, if we say we have a molecule here, it has some, and I'm going to put translational in parentheses, it has some amount of electronic energy, whatever the energy from this HOMO level happens to be. It has the energy from this vibrational level, V equals 2, and it has the energy from the rotational level, which is J equals 4. And so a full description of the energy of this molecule requires these plus this kinetic energy. So with the now try this, there are, like I said earlier, there are no problems corresponding to this context. This is really background information. I need you to have a conceptual understanding of how energy is stored in molecules so that we can start beginning to try to calculate how much energy a molecule has. So stay tuned for the rest of chapter 2.